Welcome back to the summary workshop on applied resurgent asymptotics, hosted in hybrid mood by the Isaac Newton Institute. Our first speaker this afternoon is Tomas Reis, and he was educated at the Instituto Superior Técnico in Lisbon. He studied at the Perimeter Institute in Ontario, and he's now completing his his PhD at the University of Geneva. And he's given us a rather exciting title. His talk is Chasing Renormalons in One Dimension. So please, Tomas, would you begin your chase?
Thank you very much. Thank you very much for the organizers for inviting me. It's a very interesting opportunity to participate in this workshop. So yes, so as introduced, my name is Tomas Reis. I've been working with Marcus Marinho at the University of Geneva, and also Ramon Miravitas-Mas, unfortunately, who also collaborated in the work that I'm going to present today. So in my talk, I'll start just by bringing up some ideas of resurgence. Of course, I understand most of the audience is already familiar with the key ideas, but just a couple of the ideas that I want to make use of, particularly just in case there's maybe a non-expert in the audience. Also, then I'll introduce renormalons. So, what is this thing that that I should be chasing? And then talk about a concrete case of how we study and what has been our work with renormalons in a condensed matter system, and then go into a quantum field theory case in a more concrete quantum field theory. Okay, so the setup is something that most of us are already familiar with. So in quantum mechanics or quantum field theory, most problems are too hard to solve exactly, and so we do perturbation theory. And perturbation theory typically gives us an asymptotic series. This is of course not new, and often is very beautifully physically motivated. As for example, Dyson argued, for example, in 53 about QED, that this perturbative series should not become convergent from physical arguments. So in some ways, one could say that the fact that quantum theory is not convergent in the series sense is not surprising, but it's still unpleasant. Even, I mean, a priori, naively, even if we knew all coefficients of these asymptotic series, we would be limited in our approximations by optimal truncation, which already feels unfair. We can do hard work and get thousands of coefficients and still be limited. Now, of course, we can do better than that. We have access to Borel summation. So we take these divergent asymptotic series, we can construct this transform typically by dividing out this factorial divergence. This gives us an analytic function, and then we can compute the exact result by this modified Laplace transform when everything goes well. Now, for those who have already worked with these problems, there are of course many ways in which things cannot go well. The simplest, for example, is just even if we just take this simple example of the A geometric factor times a factorial, if A is positive, so non-alternating series, we get a pole in the positive real axis, which obstructs this modified Laplace transform. We can then, of course, we can modify instead of integrating positive real axis, we can deform it, integrate it slightly above, slightly below, and take the limit of the angle going to 0, but the above or below will differ. And in this very simple case, it differs by the residue. So singularities in general, and of course they can be a lot more complicated, as other people have presented, they obstruct this summability, but already they can start hinting about what about perturbation theory fails. It fails because it does not account for non-perturbative physics. And so this is the great idea of resurgence, which I would like to make use of, which is this idea that ambiguities can be cancelled by the non-perturbative physics. So if instead of talking about perturbative series, we talk about trans series, so these series promoted with this transmonomial, so these non-analytic terms of z, the coupling, what it might be, so these exponentials of A over Z, which can very naturally come from non-perturbative physics. if we work with these objects, we can get non-ambiguous, well-defined physical results and truly get sort of the quote-unquote true object that we're calculating, the physical thing which exists. Now, this is very interesting already from the quantum field theory point of view, because in quantum field theory, truly what we master is the perturbative physics. It's really what we master. And non-perturbative quantum field theory is still how to define it rigorously, how to properly construct it, still an open mystery. And resurgence seems to give us a path to get non-perturbative physics from perturbative physics, which is what we know. Or even in a more simple, pragmatic, this is also a great exploration tool. We can use the asymptotic behavior of perturbation theory to probe non-perturbative physics. Of course, there is a lingering question, which I will very much not even attempt to answer today, but which is, for a given quantum field theory, can this trend series be constructed from first principles? And I mean, we would love to know the answer to this. I mean, if we could construct this trend series from first principles in a certain way, we would have non-perturbative quantum field theory sort of in our bags, but we still don't know how to do it. Now, and why not? Why can we not construct these things from first principles? So why are these series factorially divergent in the first place? So perhaps I'm talking about quantum field theory and quantum mechanics. When I talk about perturbation theory, I usually mean things which can be computed from Feynman diagrams. So, for example, when there is an instanton effect, what happens is that we have a factorially divergent number of Feynman diagrams that have a given order due to some combinatorial, typically due to some combinatorial phenomenon. We have n factorial Feynman diagrams, and then each of these Feynman diagrams is more or less, let's say, order 1 once we integrate in the phase space. Once we integrate in the phase space. But this is, of course, not the only way that these series can be factorially divergent. We can also have an order 1 number of diagrams, which are themselves valued n factorial. And by this, I mean that once we do the moment integration at each order is n factorial, even though the number of diagrams at each order is, let's say, order 1. So this is what is called, in a certain way, this is a perturbative definition of what is called the renormalon effect. The series is factorially divergent because at each order there is a particular, or 2 or 3, but a constant number of Feynman diagrams that are valued n factorial, and here n being an order n, they're valued n factorial because of phase space integration. Now the name is of course a bit deceptive. The on part is of course the particle. It was baptized in analogy with instantons. And the renorm part, they were originally identified in renormalizable theories, and renormalization does play a big role in sort of like the classical theory of renormalons. And so this is a typical. So here, when I say, so what do these diagrams typically look like? It is factorially divergent. So here, divergent. I will always use divergence in the sense of a series, not in the sense of Dirac or something like that. So this is the typical diagram that contributes with n factorial. So for example, in particle physics, renormalon effects often appear in these computations of these currents. And the diagrams that contribute to renormalons often look like this. So things with many bubbles. And then we have some sort of logarithmic divergence close to the UV or to the IR that makes the momentum integration become n factorial. Now, I understand this definition is a bit unsatisfactory, or a bit frustrating. First of all, I kind of also introduced instantons in a weird way. I mean, you probably don't think of instantons as combinatorics of Feynman diagrams. You think of instantons as subtle ones. You think of instantons as these non-trivial solutions to the Euclidean equations of motion that have finite action. And that can be very strongly motivated from a semi-classical analysis with path integrals. So we can construct instanton sectors by expanding around other saddle points and doing perturbation theory around other saddle points. So from the instanton point of view, even this transition feature is very natural. The same thing, unfortunately, cannot yet be done for renormalons. There is, however, I mean, there is very interesting work by Untitled and Boone in that direction, in trying to understand renormalons from a path integral point of view. But as far as I understand, I mean, this is still a conversation which is ongoing, and we still have not truly. I mean, there is still a lot that we have to understand about renormalons. But there are cases where we can where we can make a little bit more sense of them. So for example, if we have access to an OBE analysis, which is often the case, for example, in this current analysis in particle physics, renormalons do seem to be tied with the non-trivial condensates in the vacuum. So in this OBE, we very naturally get this vacuum expectation values of other operators that from perturbation theory you would expect to be zero, but actually have some non-perturbative value. And this non-perturbative value seems to be related to these instant-on effects that we observe at the level of Feynman diagrams. And we can also motivate this more or less from RG, as it happens in asymptotic tree theories. And perhaps one of the most important motivations also to the instants, even if they were not common, one theory that we know that has renormalons is QCD, which is, of course, physically very important theory. And actually, in QCD, the dominant pole in the Borel plane is the renormalon, not the one from instance. So if we cannot yet construct them from first principles, it is not clear how to motivate them from path integral. And the OBE analysis is only something that we have in certain cases for some observables. How do we even know for sure that a theory has a renormalon effect? Of course, the answer, the simple answer is, well, we just have to look at the asymptotics of perturbation theory. But this is naturally very hard to get. I mean, we're talking about theories where you have to compute non-trivial Feynman diagrams. So, I mean, computing Feynman diagrams to order 3 can already be very hard. To order 10 can be a research program. To get the asymptotics the asymptotics with any precision, we would have to compute Feynman diagrams for order 20 or order 50, which is not really tenable. But of course, we can do smarter things than just compute Feynman diagrams. There are 2 things in particular that people have made use of, and that we have also made use of. One of them is that if we have other limit, other than just sort of weak coupling, other than the parameter that we take to be small in perturbation theory. A typical example of this would be large N. Large N can be extremely useful at simplifying perturbation theory. For example, we might introduce a large N at the latter stage just to single out diagrams, and then we don't have to compute actually all Feynman diagrams in the theory. So large N is one of the tools. But then the other tool that we would like to make use of, which has also been motivated over the years by many people, is integrability, which is the reason why ultimately we work in one dimension. And here, when I say one dimension, of course, I mean for condensed matter systems, I'm thinking of things in one space dimension, and for quantum field theories, I'm thinking of 1 + 1 dimension. So this is the realm of integrability techniques. Integrable techniques, of course, they're extremely powerful because they give us an exact solution to the problem. But in the correct settings, we can take that exact solution and expand it around some sort of weak coupling limit, take the perturbative expansion of the exact solution. But thanks to the integrability, we can find results in ways that don't involve computing a very big number of Feynman diagrams. And here I find this quote by Freeman Dyson extremely, let's say, very motivating. Sorry, very motivating of sort of this philosophy of looking at the simple one-dimensional integral models. Some time to read it, and so with this in mind, so how can we get perturbation theory out of integrable techniques? So there is one particular recipe that we've grown fond of. So what happens in many of these integral models is that their ground state can often be described by a Bethe-Ansatz integral equation. So there's some integral equation where f is some function that encodes our ground state in some way. K and G are specified by the model, and B is the parameter that will ultimately also encode sort of the weak coupling. And for these type of equations, Volin in 2009 proposed an extremely powerful method where we can expand this integral equation has a power series in the weak coupling limit, which turns out to be 1/b. B goes with 1 coupling more or less. And so we can expand this integral equation. We can manipulate this integral equation to give us the solution has a power series in 1/b. And then by playing around with this power series, you can get several observables from F and ultimately write things in recognizable, in a recognizable perturbation theory, with the regular couplings that we're used to. Now, what happens in practice is that it turns this integral equation into a set of recursive algebraic equations. So this is good in the sense that it's algebraic equations which can be solved exactly. We can get exact coefficients. I'll show some a bit more ahead. So we can get these exact coefficients. We can just run it. This becomes a problem of optimizing Mathematica. But if we do this exactly, it becomes exponentially more complex. So the time that it takes to calculate the coefficient grows exponentially, and exponential growth, as we have also recently become even more strongly aware of, it's very unpleasant. So already at order 50 for most models that we studied, already at order 40 or 50, it takes about a week to compute just one coefficient. Now you can also approach it numerically, and numerically this can be a lot faster. And the collaboration of Abbott, Bajnok and friends have pushed this numerically to truly high order, to truly high orders for the O4 sigma model. So this method is extremely, this method is very powerful. It's extremely useful at getting high orders in perturbation theory in these integral models. And so what can we do with it? So what is a concrete example where we can use this method to learn something new, So let's start by an example in condensed. So the Gaudin-Yang model is a one-dimensional gas of fermions. So these are spin 1/2 fermions, so two components, spin up, spin down. They're in a circle, and they have an attractive delta function interaction. So this model has been studied for a very long time. It is one, if I'm not mistaken, the first or one of the first applications of the nested Bethe ansatz. It is integral thanks to this delta function interaction. It has a dimensionless coupling gamma, so this parameter which I'll be using later, so which is just the regular coupling that comes with the delta function divided by the density. And a curious aspect from a condensed matter point of view of one dimension is that in a one dimension, the dilute limit would be strongly coupled, while the weak coupled limit would be dense, which is a bit counterintuitive for compared to what happens in models that higher dimensions. And so this system is integral. So if we take the limit where the L, the length of the circle where this gas lives, so we take it to infinity, we take the number of particles to infinity and the density to finite, we get some sort of thermodynamic limit where this nested Bethe ansatz becomes integral equation, exactly of the form where this method by volume is applicable. So we get, and it's an integral equation which is actually deceptively simple. It just says this x minus 1 squared plus 1. But this integral equation has actually been known for a fairly long time, and it is the weak coupling limit of the strong coupling limit of this equation is actually more or less tractable, but the weak coupling limit was a very difficult mathematical challenge. From a rigorous point of view in mathematical physics, people had gotten 3 coefficients in the perturbation theory, for example, of the ground state of the perturbation theory in general, of the ground state energy in particular. Numerically, people had gotten something like 10 coefficients. So this equation is, despite the simple, so of course we could also solve it numerically, but that is not very insightful from our analytic research point of view. And another important aspect of this model is that though it was originally introduced for a spin 1/2 fermions, we can quickly generalize. It was quickly generalized to the case with n spin components. So instead of just having spin up, spin down, we can have n spin components. These will be of use later. Okay. So we take Volin's method. So we take this deceptively simple integral equation. We transform it into this recursive set of algebraic equations. But let Mathematica solve it for 2 weeks, and we get these exact coefficients for the weak coupling expansion of the ground state energy, which we can compute from this method. Now I put the coefficients. So these coefficients to arbitrary order, they all end up being these polynomials of zeta functions of odd numbers. which I'm not an expert on, but I think it has. But some other people have remarked this comes from some interesting number theoretical properties of the system. So we can get them to order 50. Of course, Bowling's method is coherent with the previous computations, of these coefficients. And so we take them to order 50 and we look at the asymptotics. After all, that's where the resurgence magic shall happen. And at leading order, we can numerically fit more or less very confidently at leading order the behavior of these coefficients, and they go with this pi squared geometric vector times this gamma of k. So first and foremost, it's an alternating series which is factorially divergent, so it is not Borel sum. And this pi squared determines the scale of our non-perturbative physics. So, okay, so we take this condensed matter system, we look at the perturbation theory, it is not Borel summable, we need non-perturbative physics to make sense of it. What could be the non-perturbative physics of this system? No. This is not actually a mystery. If I take this model to a condensed matter physicist and tell him that there is a non-perturbative scale in the system, he or she would quickly let me know of what is the scale. And the scale, what would be scale? Which is superconductivity. So this is a fermion gas within this is a fermion gas with a this is a fermion gas with an attractive potential. So even when we are doing perturbation theory, even starting from an integrability point of view, but by taking this weak coupling limit, what we're doing is essentially expanding around the free gas. But the ground state of a model, of a fermion model, is attractive two-spin fermions with two-spin components and attractive potential. Its ground state resemble it should be modeled as a superconductor. It will not be a gas of free particles. It will be a gas of Cooper pairs. So the spin up fermion and the spin down fermion bound by this attractive potential. So this is exactly the nature of the BCS approximation, which we can also apply to this model, which we can essentially think of it as a variational method, where we approximate the wave function of the ground state by a gas of these Cooper pairs, instead of approximating it by sort of free particles, as one would do in the case of a free gas. And in that case, and the BCS approximation gives us a gap equation, which is essentially an equation to find the BCS gap. So this would be the binding energy of these pairs of spin up, spin down fermions, and lo and behold, we get this pi squared factor. Yes, we do get pi squared over 2, but actually even within the BCS approximation, which unlike integrability, it does not give an exact result, since an approximation that is very good in the weak coupling limit. For the ground state energy, the gap should actually contribute as gap squared. So we can all heuristically see this in the BCS approximation. So n gap squared gets us exactly the pi squared over gamma. So it seems like the non-perturbative physics that is manifesting here is superconductivity. Now, I introduced a bit this dichotomy that series can become factorially divergent either due to incident effects or due to renormalon effects, which of course, I mean, we're not very sure. The complete dichotomy, but to understand it has a renormalon effect from its ultimately perturbative definition, we have to look at Feynman diagrams. So again, computing Feynman diagrams, of course, it's hard. So we have to somehow find a way of singling out a family of Feynman diagrams that account precisely for this pi squared times factorial behavior, and that we can argue that indeed it comes from this family of factors. So here comes the ring diagram. So ring diagrams are already nothing new. They're well used in condensed matter physics, for example, in RPA analysis. And they have a lot of very interesting properties. First and foremost, and perhaps most important, that in one dimension they're factorially divergent. So factorial divergence in this sense that the diagram with n bubbles contributes it n factorial, and this is essentially due to logarithmic divergence in the II. So perfect. I say here in one dimension because actually the DCM diagrams in higher dimension generalizations of the model would not be factorially divergent, but there are other families in those cases, but we'll leave that for a bit later. Of course, this being a fermion system, we could always have wild minus signs running around. So maybe one could argue that maybe yes, so they are factorial divergence. Of course, they could cancel with something else. They could be somehow modified by a Donder family of Feynman diagrams. And so we can actually isolate them by taking this parameter of the number of spin components. So the system can be generalized to have n spin components instead of 2. And we can take, and already doing this, the dependency on n isolates these diagrams, and in fact they are dominant. So if we take the large number of spin components limit, we get exclusive at leading order, we get exclusive with these diagrams. So that way we know we can protect them. In a way, and of course they come with the right weight. So they not only have to be factorially divergent, they also have to be factorially divergent times these powers of pi square factor. And this is exactly what we get. So this seems to show that at least in this model for now, superconductivity manifests itself in the weak coupling expansion has a renormalon effect. It is a weak coupling expansion which is not Borel summable. It's not Borel summable, and at the level of Feynman diagrams, it comes from this phase space integration. So it seems to me a renormalon effect. Is this a particularity of this model? Well, we suspect not. So already because we see this for the two spin component case and n spin component case. This already in the n spin component case, this pi square factor becomes pi square over n, so it becomes a bit non-trivial. And there are other models where we can observe this. So we have the one-dimensional Hubbard model, which is also integrable, which has a particular limit. The half filling limit is a particularly interesting case from the point of view of resurgence, because it is a model where the perturbation theory is non-trivial. The coefficients are fairly rich, and yet the exact coefficients are known to all orders. It's the result already from the 70s from Ovchnikov and Colin Raiders. So this was the results are so that the coefficients are actually known to all orders, and there we also see this effect. So this is also a system which is in its attractive regime. It's a system for an attractive coupling. It has a superconductor behavior. It has superconductor behavior, and indeed we can calculate the gap, and indeed the square of the gap corresponds to the first pole in the Borel plane. In the Borel plane of the transform of this perturbative expansion, the ground state energy. We can take the Hubbard model with n spin components, with n is larger than 2. So this is a model which is not integrable, but we can generalize the things that we have learned from studying this model. So for example, this ring diagram analysis and this large n analysis, and then we also observe this relationship. And lastly, though, while in higher dimensions, we cannot verify this correspondence between the square of the BCS gap and the particular family of diagrams. As I said, one of the reasons is that, we can no longer use these ring diagrams. And so in higher dimensions, there's a lot of candidate families of interesting Feynman diagrams. There are several families of Feynman diagrams which are factorially divergent, and they do have integer times pi squared geometric factors, so they do hint that the effect is similar. But unfortunately, there the picture is not so clear. We cannot finish and complete the picture to truly univocally say this, but it seems to point in the same direction. And so, what is this direction? So, what is this? What do we learn from all of these condensed matter models? Is that so there is this idea that in a superconductor, perturbation theory should not be good. It is this idea of the Cooper instability, that the free gas is ultimately an unstable configuration, and it's all perturbation, and one would expect the fermions to start pairing up and forming Cooper pairs. And the way this manifests mathematically seems to be that it manifests in the fact is that this perturbation theory, while a perfectly valid asymptotic series that we can take the numerical solution of the Bethe sets and see very much that they perfectly fine asymptotic series that fits very well. It is ultimately not Borel summable, and it's not Borel summable exactly because we see superconductivity manifested, and we conjecture that there's a relationship between the square of the BCS cap is actually somewhat general. So this is and there's also an interesting case of a renormalon. So because this is also a renormalon in a setting which is completely different from the setting that we were used to seeing. So renormalons, we're used to thinking about renormalons in asymptotically free theories, which of course there's a relationship between the Gaudin model and asymptotically free theories, but we're thinking more so like quantum field theory, particle physics. And here we get the renormalon effect in a quantum many-body system where no RG is necessary, diagrams are fine, Feynman diagrams are finite, there's no need for thing reactors. We can say the computer, they come with values, there's an external parameter, and here we get a renormalon effect. And so we get the renormalon effect tied to this interesting non-perturbative physics of superconductivity. Now, before I look into, before we start moving a bit into some comments about the quantum field theory, there's other interesting lessons that can be taken from it in this method. So the Gaudin-Yang model has a bit of, let's say, a cousin, the Lieb-Liniger model, which is another very old model that has, thanks to Lieb-Liniger, it is also integral, but it has a particular difference, which is a model of bosons. Instead of fermions, the integral equation is basically the same as the Gaudin-Yang model, except for a sign, but that sign is actually, of course, very critical. We can also apply this method to it, get the perturbation theory for the ground state energy. It is not Borel summable. It's factorially different. Now, this being bosons, one could more reasonably suspect that instantons. I mean, for the fermion case, there were some arguments to rule out that instantons would be the cause of this divergence, but for bosons it could more reasonably be the case. But at least we're talking to some PDE experts on this, and there doesn't seem to be a finite action solution to the Euclidean equations of motion. And in fact, we suspect that there is also unfortunately there we don't have a large n limit for technical reasons, but we suspect it's still a renormalon effect, and we suspect that here we start transitioning a bit into quantum field theory. Because we can take the relativistic analog of this Lieb-Liniger model, which is the ON linear, it's the linear sigma model. So it's the ON vector model. So it's essentially the model that we all use to learn about, to learn about Goldstone bosons. But when into dimensions, it becomes the relativistic analog of the Lieb-Liniger model. And there we can take the large n limit, and we find that indeed at the large n, it's again ring diagrams that dominate, and they are factorially divergent due to space-based integration. And so there is a renormalon effect in its perturbation theory. And this is a very curious aspect because this ON vector model, it's a super renormalizable theory. So even this idea that in quantum field theory, renormalons are a property of renormalizable theories. There's not so much case. In this linear sigma model, we have a renormalon, and hence we also suspect that we would have a renormalon for the Lieb-Liniger model because it's the non-relativistic limit, and it is a super. But this vector model is a super normalizable theory. Now, there's some interesting story here about the non-perturbative physics of this seems to be related to the Coleman-Mermin-Wagner theorem. In the end, if we have time and someone is interested, we could discuss this. But I would actually like to move to a different example in quantum field theory, which has actually taken more part time, which has also taken some more time, which is these asymptotically free integral quantum field theories. I call them psychedelic from motivated by this quote of Freeman Dyson. So asymptotically free integral quantum field theories, and perhaps for many people, what I'm going to say now, It's obvious, but for those less familiar, so these are what one calls one-dimensional theories, which are extremely rich. So they're integrable. So there is an exact solution, for example, for their S matrix. But at the same time, being 1 plus 1 dimensional, there are a lot more factors. And so they have been studied a lot as toy models for QCD, and now more recently they've become also very, very popular because they appear in AD, they appear in AD and CFT, for example, and in other string theory applications. So they're a typical theory which is simple enough to be tractable and at the same time extremely rich and give very interesting, difficult problems. And here there are many theories one could describe. So here I'm particularly thinking about the nonlinear sigma model. It's a supersymmetric extension, the Gros-Neveu model, and the principal chiral field. These were the models that we studied, which we studied more deeply. But of course, one also has the CPN model and other cousins of these four. Now, so how do we bring out this setting to extract the renormalon analysis, a renormalon analysis from these theories? So one problem is that this being asymptotically free theories, the coupling, the couplings run as we're familiar with, and so this weak coupling expansion is going to need some sort of external scale. One way of thinking, for example, the analog way of what is typically, for example, done in more particle physics applications would be to study, for example, observables that naturally have an external scale. So, for example, something like a current that has the momentum. But this would take as much use of the integral properties. And so there is this old idea, which is to take these models and couple them to some external chemical potential, which will in a way set this external scale, which is tunable. And then this chemical potential essentially couples to one of the charges of the model. And then, since we know their exact X matrix from integrability, we can get to describe the ground state of these theories in these settings. It comes out as an integral Bethe of this form. So the M-cosh part applies to all of them, and it's the K, the kernel is going to be the part that depends whether it's the sigma model or the Gros-Neveu model. And of course, the properties of the K will very subtly change the behavior of this integral equation. So this is an old idea, of course. So it goes back to Polakov and Wigman, and it was extremely fruitful, for example, in the 90s to calculate the exact mass gap of these theories. So you have to assume that the theories have a mass gap, but you assume the theories have a mass gap, you get this integral equation, and then by comparing it to regular Feynman diagrams, for example, you can get the exact mass gap of the theories. These were exactly the sort of integral equations that the Volin method. In fact, Volin presented his method originally for this ON sigma model. So we can generalize the Volin's method to all of these models, and so get the perturbation theory, and here get the exact perturbation theory. So these would be the equivalent of having, so we're avoiding having to compute way too many Feynman diagrams and get it exactly for a finite n, for example, for a finite n, and get the exact coefficients with all these nice zeta functions. And so what we find, and what did we expect? So we expect, so these are the type of theories where we expect there will be renormalons. And so, for example, these are the type of theories where one can do this OPE analysis. And what happens in this OPE analysis is that there is non-perturbative, these non-perturbative condensates, they are non-perturbative, so they come with this exponential of something over coupling squared, and this something is determined by the classical dimension of the operator in the condensate times beta 0, so this would be the beta function of the coupling, times an overall power of the coupling. But this power of the coupling is already very sensitive. It's sensitive to one loop, so it already senses the second coefficient of the beta function, and the anomalous dimension of the specific operator, which condensates. So from this OPE analysis, one would expect that renormalon effects exist in this theory. Now, of course, there is an important subtlety, which is that before Voling's method, we study the ground state energy, and for the ground state energy, we cannot do an OBE. We cannot do an OBE analysis. So these predictions are in a way they're a bit heuristic. They're a bit heuristic, and what we find is that in the end, these coefficients of the ground state energy, which we extract using Voling's method, actually do follow the predicted asymptotics from this OBE analysis. So they have a geometric factor to k, which is precisely this d over 2 beta 0, d over 2 beta 0, and then we have this gamma function. So for example, in the ON sigma model, if we take 44 coefficients, we can fit very well the leading singularity in the positive real axis of the Borel plane. And we get something which is precisely consistent with an operator with classical dimension 2. This n0 is 0, and this n0 is just an offset, multiply and multiply. But this delta, which has us always sensitive to the anomalous dimension, and we get this very specific delta of 2 over n minus 2 minus 1. This is precisely consistent with what is actually the only good candidate at dimension 2 for this condensate, which would be the Lagrangian operator. So we get this fairly non-trivial check of Renormalon law by applying Voling's method. So an analogous thing happens for the Gross-Nouveau model and the non-supersymmetric, and the supersymmetric nonlinear sigma model at the principal chiral field. So we get this validation. So we get this validation of this classical of this Renormalon predicament. Even though a lot of these predictions are often motivated by this OBE analysis, and the ground state energy is not amenable to an OBE. So there is, of course, here again this question of first principles. There is an open question of how to motivate from first principles. How to motivate from first principles these non-perturbative physics and the ground state energy. How can we perhaps construct it using perhaps some limit of the OPE, or perhaps using the tools of integrability. That's another big question. So we can get the perturbative series from integrability. Can we also get these non-perturbative physics? And this is still an open question. Of course, it would also be interesting to also double check that these things not only correspond to the scale that is predicted to be a Renormalon effect, but to actually check that they come from ring diagrams and have some more analytic control of this, because I mean ultimately this verification is to some degree, while the coefficients are exact, we can only get the coefficients to order 44. So there is still some numerical setting to this. And in fact, in the sigma model, so for the Gross-Nouveau model, there are old results that also validate this in the large n limit. Also for the ON sigma model, there were also. It's also in the large n limit there should be Renormalon effects, but what we also did was to take the large n limit, but after already being in the context of perturbation theory, because often in the large n limit we take the large n subtle. But something else that we can do is take the limits and take the perturbative and take the perturbative expand around the perturbative fact, so around the triple cell point. And then take the large n limits to single out only a certain family of diagrams. And for example, in the large n sigma model, we see that this large n limit applied to a perturbation theory around the three-fold vacuum isolates precisely these ring diagrams. I mean, isolates these ring diagrams. Of course, these are ring diagrams in a certain definition of the fields. But the point is that we can analytically see this Renormalon effect in the sigma model coming from this momentum space integration of Feynman diagrams, and we can validate analytically in the large n limit these results, this numerical fitting that we get from the exact coefficient from Voling's method, and we can also do this for the supersymmetric nonlinear sigma model. Now, this is particularly interesting because the numerics of trying to fit the asymptotics of the supersymmetric nonlinear sigma model were actually very tricky. The renormalon effect there is extremely subtle. But in fact, we can see, but doing this analytically and looking at ring diagrams, we can see analytically that the series for the ground state energy, for example, is not Worrell summable. So even a supersymmetric model is not Worrell summable due to a renormalon. So not even models that we expect one could expect to be simple turn out to be impervious to these renormalon effects. And so with this, perhaps I could start wrapping up sort of like the key ideas. The key ideas that I would like with this talk. So of course, the first one, which perhaps I don't have to struggle, is that resurgence is an extremely useful tool to make sense of non-perturbative physics, to make sense of the perturbation theory that we have in quantum field theory, and how to put them together. Who knows? Maybe even go towards a road of one day getting a rigorous non-perturbative definition of quantum field theory. And in this picture, we have to take into account instantons, as many of us are already familiar with, that we have to introduce instanton sectors, the perturbations around instanton sectors, but renormalons are also a key ingredient. We will not understand the quantum field theory non-perturbatively until we understand renormalons. And ultimately, we also need to understand, for example, QCD numbers. And renormalons are far more common than perhaps was previously expected. So just today, so we have studied renormalons in the condensed, we have studied condensed matter systems, in super renormalizable theories, in renormalizable theories, in supersymmetric models. And in fact, there has been this group which has found a renormalon in a quantum mechanics case. So renormalons are truly a big problem of quantum theory in general that we need to understand better. And one way of understanding them better is, of course, to start with interesting pi models. And integrability can be an extremely powerful tool to do this. And an extremely powerful tool to do this and to give us both the perturbative series, and who knows, perhaps it will give us also more clearly the origin of these non-perturbative effects. And lastly, that condensed matter is also a very interesting lab for both for renormalons, for this renormalon analysis, and for resurgence in general. So the study of the Gaudin-Yang model was one of the first, I think, applications of resurgence to condensed matter, which means that there's still a lot more cases to be studied, and a lot more cases where the tools of resurgence can be extremely enlightening. And I mean, one thing, not really a strong motivation, but at least I find it a bit of a nice little aspect, is that when we use, for example, resurgence tools to identify non-perturbative physics in condensed matter models, one could actually run into something that could be measured in a lab, which is a bit, which is a little bit of a different surprise. I mean, of course, I'm not saying that realistically this could happen, but it also connects to very much physical systems that one can build and study in study and probe in many different ways. So with this I wrap up. Thank you very much for your attention, and I hope there are questions.
Thank you for this very thought-provoking talk. It is now open to questions.
Can I make a question?
Yeah.
Please.
Actually, two questions, Tomas. Excellent work, by the way.
Thank you.
The first one is, so if it's not renormalization that asks for renormalons, what should I think of as the guiding principle that is asking for renormalons? And the second would be, did this bring us any closer to understanding the semi-classical description of renormalons? Whatever that.
Okay, those very good, very good. Good question. So the first one. So it is not entirely clear. I wouldn't rule out that at least in some cases renormalization is a guiding principle. is a guiding principle for renormalon. So, for example, in the asymptotically free theories, I mean, the renormalon effect seems to very much related to the dynamically generated scale, and at least for me, and perhaps I'm being too naive, but at least for me, it's hard to think about the dynamically generated scale without thinking about renormalization in some way. So I do think that renormalization plays a part, and for example, in many of these models, and even in the condensed matter models, perhaps, and so there's an interesting open question that one could investigate. So one can make renormalization appear in these models, right? So one can study. So for example, one can study these models very close to the Fermi surface, and very close to the Fermi surface, suddenly we can introduce this Wilsonian renormalization. And in that perspective, for example, one can motivate these BCS gaps or these gaps that we find in the Gaudin-Yang model. One can motivate them from essentially RG arguments. From essentially RG arguments next to the Fermi surface. This was actually, I mean, this is always the work of Larkin and I forget the second. I mean, I have some slides here, but anyway, but yeah. So it could be that the condensed matter models that have renormalon effects have some RG picture of them hidden in some sort of limit. So I wouldn't rule out completely that renormalization plays an important role in many of the cases, but perhaps not all cases, because for example, the linear sigma model, there it is not clear at all to me what is the role that renormalization is playing. So it could be that in most cases it is renormalization plays a role, and then there are some other special cases that we have to pay attention, and then maybe we need some other picture to connect the two. I don't know. I think that's one of the interesting open questions to clarify. Sorry. The second question.
Semi-classical.
Oh yes, sorry. Semi-classics. This gives us some interesting. I would say that we already have some hints of how this gives some hints of possible roads, At least for example, in these integral models, I mean, these integral equations, for example, are extremely rich, and it is probably this Boolean method does not exhaust all the information that these integral equations hide. So there might be a way of extracting in some semi-classical way the non-perturbative, at least for these integral model cases, and that would already perhaps give us an interesting picture for then take to the higher dimensional, more complicated models. I mean, of course, there's the other than that. Well, I would say that there is still perhaps some work to be done also in the condensed matter front, because maybe there is a way of constructing semi-classics perhaps by looking at some other ways of looking at superconductivity or at these gaps. Perhaps I think there is at least a hint that there might the condensed matter models might give us interesting hints about how to construct these things semi-classically. I mean, I cannot give you a concrete answer right now, but I do think that at least that is a direction that might be interesting to look into. And in fact, I mean, historically, this interplay between quantum field theory, between condensed matter and particle physics, there's a lot of history to it. So I would hope that maybe there could also be some interesting insights, but there is not. I don't have anything concrete in that aspect right now.
Thanks very much.
Are there any more questions?
I have one question.
Please,
Oh,
Yeah. So can you explain a bit how you make a difference or disentangle the effect of instantons and renormalons? How do you know it's a renormalon?
yes. So that's a very interesting non-trivial question. So for these integral models, we rely often on cases that rule out instantons. So for example, you can rule out instantons by looking at the equations of motions and verifying that there are no candidate saddles, or if they were, they could not contribute with these scales, right? Because they also contribute with very specific scales. For example, this d/2 beta 0. this also would have to be a very particular instanton, right? It would be a very particular action. But I think, at least for these ones, I think you can just rule it out. You can just rule it out on the existence, or rather the non-existence of instantons in the theory. In the condensed matter theory, in the condensed matter system, it's a bit more non-trivial. We can resort to several things. One can resort to just straight up studying the PDEs, and trying to verify, or at least try to check as much as we can that there are no finite action solutions. For the fermion models, there were also some Feynman diagram arguments made before, and in fact, in similar and a bit, well, this is not a watertight argument, but in similar models, usually with these fermion models in condensed matter, often instantons are not strong enough. They don't actually go with n factorial. They go something like an n factorial over 1 over 5, I think, but some less than truly factorial. But which is why it's also interesting. Which is why it's also interesting to have this Feynman diagram picture, and also these connections to OB, to the OB, and to the RG to check that indeed this is something which fits into the renormalon picture, not to the instanton picture. But it is something which is delicate. I agree.
Okay, so we've heard about this intriguing idea of renormalons without renormalization. Can I ask you about ultraviolet renormalons in field theories and their critical dimension? If you go back to your figure 1 on slide 3, please, Tomas.
Yes, sorry. Yes.
Okay, so let's think that this is an ultraviolet renormalon in quantum electrodynamics. It's the asymptotic photon propagator. I calculated that next to leading order 1 upon n correction 30 years ago to all orders in perturbation theory in terms of zeta values. The point that I want to make is that if you just look at the beta function in the minimal subtraction scheme, these ultraviolet renormalons completely go away. And that's directly relevant to the question of critical exponents, because it is the minimal subtraction scheme that we have to use to get the critical exponents. John Gracie and Eric Pencer have been looking at this. And in Phi to the 4th theory, where we have the beta function up to 7 loops and very good estimates up to 12 loops, we see a clear situation, I think, in which the instantons are giving the asymptotic behavior, and there's no problem with ultraviolet renormalon at all because we're looking at critical exponents. So I think that fits in with your picture. Now, of course, the big question is look at QCD, or phi cubed in 6 dimensions, where through asymptotic freedom and dimensional transmutation, then you have e to the -1 upon g squared corresponding to bar corrections to the OP of your said. But I recommend this question because it's been actively debated. There was a specialist meeting on it in Liverpool last week, is are the critical exponents of field theories in their critical dimensions free of ultraviolet renormalon effects? Do you have an opinion on that?
No, unfortunately, I don't have anything interesting to add, but thank you very much. I mean, I'll look into it.
Okay, so thank you for excellent timekeeping. Would you please switch off the recording?